All right, Cauchy-Euler differential equations. So we're going to assume that we have a homogeneous one to start with. And again, I'm assuming there's a 1 here because you went through and divided everything by whatever was here. You went through and divided everything by it. So you can just assume there's a 1 there. We could have done that in the constant coefficients case too. It might have made things simpler. And then what's the guess going to be? Not e to the lambda t. This time it's going to be t to the m. So guess x of t equals t to a power. And the power actually does not have to be an integer, but it could be. So it could be like t squared, but it could also be t to the 1/2. That would be square root of t. So that's going to be our guess. And we might even allow the power to be even more interesting than that. All right, so just like with constant coefficients, when you guess e to the lambda t, you put in the guess and then you see what conditions on lambda need to hold for the differential equation to hold, for you to have a solution. Same here, but with m. So I could have called it lambda, but for some reason we're calling it m. I don't know why. Okay, so to put in our guess, so the main question is, what must m do for t to the m to be a solution? So to put in the guess, I need to know x prime and x prime prime. Well, that's easy. X prime of t, just use the power rule. The power rule works even if m is not an integer, right? Like if it's square root t, m would be 1/2. Then this still works. And x prime prime would be m minus 1, t to the m minus 2. And are you seeing why this is good? So when I substitute these in, there's going to be a t squared multiplied by the tm minus 2. There's going to be a t multiplied by the tm minus 1. And there's just going to be a t to the m there. So there's going to be an overall factor of t to the m, which will cancel away. So that's the reason for that guess. So let's do it. Let's put in these things. So the dE now becomes t squared times m minus 1 t to the m minus 2 plus b times t, so I'm just copying this stuff down, b times t times x prime, that's m t m minus 1, plus c, and then x, that's t to the m, equals 0. And of course, t, so like t to the m minus 1 times t. This is m minus 1 t's multiplied together, and this is another t. So when you multiply them, you're going to get t to the m, right? So the left-hand side here, there's this overall t to the m. This has a t to the m, this t times that is t to the m, and t to the m minus 2 times t squared is t to the m. So we've got this. And now I can divide both sides by t to the m. That works as long as t is not 0. T equals 0 will actually kind of cause problems for our solutions, but we might just stay away from t equals 0. So if you look at the original differential equation, if you let me leave that comment for the end, actually. But to do this dividing by t to the m, I'm sort of assuming t is not 0. So I might have to worry about or stay away from t equals 0 later. Just going to keep that in mind. Okay, and now I've reached a quadratic polynomial in m. Right? My original question was, what must m do in order for me to have a solution? It has to be the root of a certain quadratic polynomial, right? So this is a quadratic polynomial, like m squared minus m. Let me combine those terms so that I have b minus 1 times m plus c, right? It's a quadratic polynomial in m. And there are 3 possibilities for a quadratic polynomial. Either it has two distinct real roots, or it has a repeated real root, or it has complex non-real roots. And so, again, we're going to get three cases. To think about. So let's say you end up in case 1, and there are two distinct real roots. Let's say m1 not equal to m2, roots of this polynomial here. Real roots. Then t to the m1 is one of our solutions, and t to the m2 is another one of our solutions. And if these are distinct, then these functions end up being linearly independent. So our general solution is just going to be c1 times that plus c2 times that. And there we are. So that's case 1. In case 2, you have maybe repeated root m. Then your problem is that you only have one solution, and that's not enough, right? You need two linearly independent solutions. So you can't just be like c1 times this, that's the general solution. No. Now you would be unable to satisfy initial conditions from this situation. There would be many initial conditions that you would not be able to handle. So you really want two linearly independent solutions. And do you remember what happened with this case of repeated roots when we had constant coefficients? Back then, when we were guessing e to the lambda t, if we have repeated lambda, what do? Well, I gave you this kind of unsatisfying solution, which is the other one is just t times e to the lambda t, right? Well, it's pretty much the same deal here. It's not multiplying by t, but it's equally unsatisfying. So it's going to be multiplied by, so tm, and then multiply by log or natural log or ln t, like that. And case 3, this is the really interesting one. What if you get complex, by which I mean non-real roots, like m equals alpha plus minus I beta? So it'll always be coming in complex conjugate pairs. Then what? Well, then it's still true that t to the alpha plus I beta and t to the alpha minus I beta are solutions. They're just complex solutions. And so what do we do from this situation? We wanted real solutions, right? Well, the same principle applies for a linear differential equation. The same principle applies that we used before. For a linear differential equation, if you have a complex solution, if you pick off the real and imaginary parts, then those will be two real solutions. And it will be wonderful if they are linearly independent. And they will be in this case. So let's just think about it. What in the world is t to the alpha plus I beta? What does this even mean? T to the alpha plus I beta. So just appreciate for a moment how weird this might be. Like if alpha is 0 and beta is 1 and t is 2, I might be looking at 2 to the I power, right? What does that even mean? It's kind of weird if you haven't seen it before. So, well, we're already okay with e to the alpha plus I beta, right? We know how to handle that. So the trick is to change base. So right now the base of this exponentiation is t, right? Whenever you're exponentiating, this part is called base and that part's called the exponent. So right now the base is t. We can change the base so that the base becomes e. Then we can handle it. So how to change the base? So there's a trick for changing base, which is to rewrite the base as e to the something. This is something you can always do. You can always rewrite any positive number as e to the something. Any positive number is e to the log of that number, right? Log or ln of t here. So you can think of this as a way of writing t, a funky way of writing t. Okay, and now you can use exponent rules and be like, okay, this is e to the ln t alpha plus I ln t beta. And that is something whose real and imaginary parts I can figure out. So maybe first step, let's write it e to the ln t alpha times e to the I ln t beta. And, you know, e to the ln t alpha, let me use exponent laws and look at it like this again, and then remember that e to the ln t is just a funky way of writing t. So how about I just write that as t to the alpha? To be honest, I could have done that from the very start, right? Just write this as t to the alpha times t to the I beta. I wish I had done that. Anyway, we've got t to the alpha times this thing. So e to the I times a real number. That's going to be cosine that number plus I times the sine of that number. That's kind of interesting. The solutions are coming out to be these cosine of ln of t type things, or sine ln t. Pretty interesting. Okay, now pick off the real and imaginary parts, and those are our going to be our real solutions, and they do turn out to be linearly independent. So one of our real solutions is, let's call it x1 of t, is t to the alpha. So I'm just picking off the real part, t to the alpha times this thing. And here's our two linearly independent real solutions. And then picking off the imaginary part, I get, so when I pick off the imaginary part, this is multiplied in, and I get this stuff without the I. And there we go. So then in case 3 here, if you want, you can just skip past all this calculation we did and take the end result, if you want, is that we get t to the alpha times, let's see, so what I'm going to write is a linear combination of these two, so like c1 this plus c2 that, and then I'm going to pull out the overall t to the alpha just to make it take up less space. So in case 3 I get t to the alpha all times c1 cosine ln t times beta plus c2 sine ln t times beta. Okay, so I think you now know enough probably to do the homework. So you can stop watching the lecture for today at this point if you want to. Otherwise, the next video will just be an example. And you know, yeah, in case you stop watching at this point, let me just make a comment about one last portion. If it's non-homogeneous. So like this homework problem, you have one. So I think most of your problems are just homogeneous ones. I just have to look at the different cases. And you've got some initial conditions. So you should be able to use those to find out C1 and C2. But for this one is non-homogeneous. What do you do? So the method of undetermined coefficients still works if you can just come up with good guesses. And in this particular situation, you know, you can't use the guessing table for a constant and coefficient situation, right? You're not even going to find L and T actually in that guessing table. And so use the hint for what is suggested to guess. So plug in, you know, view the left-hand side as an L being applied to X, and then plug this into the left-hand side, see what comes out. Plug 1 in, see what comes out, and then you might be able to form a nice solution. So basically the strategy being described here still works for any linear differential equation. It's just that step 1 might be too hard. For constant coefficients, it's super easy. For Cauchy-Euler equations, it's also super easy because here's how to do it always. This always works. Guessing t to the m always works. Okay, now you can stop or watch an example in the next video if you want to.